Hello, everyone. I'm Cecilia. I'm a PhD student from University of Auckland. It's a great honor to present my work for you on improving mixed example data augmentation. As most of us know, neural networks work quite well now across a wide range of tasks. One of the first successes was in image classification with ImageNet, and since then it has been applied to tasks ranging from pose estimation, robotic manipulation, autonomous driving, and playing Go, with more applications happening on a regular basis. However, most of these successes require a huge amount of data. ImageNet has 1.2 million training images. Waymo has reported driving 10 million miles in real vehicles and 5 billion miles in simulation. And AlphaZero, the most recent version of AlphaGo, trained on 21 million games, each of which has many more actual game boards seen by the network. Dealing with this requirement for large amounts of data puts many applications out of reach for anyone without a sizable budget. And it is one of the biggest unsolved problems with neural networks. One method that people use to deal with this requirement of data is data augmentation, the practice of generating synthetic data based on real training data. This typically takes the form of label-preserving transformations. And by what I mean, transformations that do not change the category or labels of the input. For example, showing here are many transforms of the input image on the top left. But some of these transformations can be fairly dramatic. They do not change the label of what type of animal it is in the image. For tasks in computer vision, typical transformations include random brightness changes, translations, flipping, and cropping, with a very long tail of plausible transformations. However, recently a new type of data augmentation was found. It breaks the assumption of being label preserving. This type, which I will refer to as a mixed example data augmentation, consists of combining two input images in some way, typically by taking two input examples and then producing one example used for training by a weighted element-wise average, showing at right. Crucially, the label of the new image is also determined by averaging the labels of the two input examples, which are presented as one-hot vectors. While this type of data augmentation does not produce the data realistic to humans, it is surprisingly effective at training models, significantly improving performance across a variety of tasks and domains, even after other forms of data augmentation has applied. Methods for mixed example data augmentation were found concurrently by a few groups, most notable the mix-up work from here at Facebook. Okay, now let's take a mix-up as an example and make this concrete. First, a random mixing coefficient lambda is randomly sampled from a beta distribution with the parameter alpha. Then we create the output example simply by taking the weighted average using lambda on both the image and the labels. For example, here, we take a 0.3 of a cat and 0.7 of a alpaca. Yields something that looks like both, or somewhat more of a weight towards alpaca. As I mentioned before, this type of data augmentation can be surprisingly effective, but it's also mysterious why it works at all. Why it works as well as it does. One guess is that mix-up creates a linear inductive bias in the model, encouraging it to smoothly vary between training examples. Another very similar method that came out roughly the same time, it is called between class learning, which I will call it a BC+. This work had the intuition of treating images as a waveform data and used the intuition from previous work on waveforms to guide the mixing process. The difference between BC+ and something like mix-up is that the mixing is done differently. BC Plus controls the variance of the output to match the input, and also try to adjust for what they call the energy of the input image. They found that this works slightly better than directly mixing the images together. Like mix-up, BC Plus consists of element-wise averaging and ignoring the variance normalization. Is essentially linear. In this work, the main question I would like to answer is the linearity critical for mixed example data augmentation? We're going to study this question empirically to give a very basic example for what a nonlinear method might look like. Consider this. Given a random mixing coefficient, just like mix-up or BC+, we can instead just combine the top fraction of one image with the bottom fraction of another image. Although this method is simple, it gives a sense that there are many other types of mixed example methods that might work. Of course, if we can concatenate them vertically, we can also concatenate them horizontally. In this work, we are going to try out a whole bunch of methods and see how they do experimentally. And if you can concatenate vertically and horizontally, we can also do something in between, which I will call mixed concat, which splits the images into 4 regions and draws from the original images in an alternating fashion. Now I'm not going to go through all the methods we tried out in detail. So here is just a quick summary for the different things that are possible. Of course, one could get a lot more creative and come up with even more approaches. But this means to provide an initial exploration of the space of mixed example data augmentation. How do they do? Let's find out. For this first batch of experiments, we're going to use everyone's favorite test bed, CIFAR10. As a reminder, CIFAR10 is an image classification task on small 32 by 32 pixel images with 10 categories, and performance is measured in accuracy or the error rate of the highest probability class. Experiments we use the ResNet18, which takes about 2 hours to train on either of the two 1080 Ti I used for the experiments. As in the original mixed up and BC Plus papers, we use alpha equals 1, which corresponding to a uniform distribution for lambda. And in these examples, I'm reporting the average accuracy over 3 different training runs. First, some baseline numbers, where we see that doing either mixed up or BC Plus improves by a little more than 1% in accuracy. And what does the simple method vertical concat do? It actually does surprisingly well, getting 4.4 error. What about the horizontal concat? Actually, a little worse at 4.7%, and mixed concat, roughly the same as the vertical concat at 4.4%. Here's a quick overview of all the methods ordered by error rate. I will go into this in a little bit of details as we answer some of the key questions. First, the main question we are going to answer is linearity critical for mixed example data augmentation? The answer is no. Actually, it turns out that most of the methods tried improved the performance over the baseline ResNet model, which directly shows that linearity is not required. This is very encouraging because it shows that the space for mixed example data augmentation might be much wider than we originally realized. Okay, but if linearity isn't critical for a method to be effective, is it a necessary component of the best mixed example data augmentation methods? So this also turns out to be not true. Here, we can look at the best performing method, random 2x2, which I didn't go over earlier, but consists of splitting the image into 4 parts. then randomly assign each part to come from either of the first or the second image, the input image. Random 2x2 is a completely nonlinear method, but it performs even slightly better than mix-up or BC+. All right, so even if linearity isn't necessary to do quite well, can we combine linear and nonlinear methods to get the best of both methods and make something even better? Yes, we can. So here is the table I showed you before, but what I didn't tell you is that there are actually two rules missing. The best method, which were called VH mix-up or VH BC+, actually combined the nonlinear methods with the linear augmentation methods, mix-up and BC+. It's performing quite a bit better than any of the other methods considered. What are VH mix-up and VH BC+? The easiest way to think about is first creating two intermediate images by vertically and horizontally concatenating the input images, and then applying mix-up or BC+ on the resulting images. That's resulting in the type of mixing patterns visible on the right, where the mixing coefficients on both top left, on bottom left and top right are potentially different. You can see that in the example image too, where the bottom left is more of a alpaca and the top right is more of a cat. Okay, last question for CIFAR 10. We have shown a variety of methods that work well, but what about the ones that didn't? My best guess for this is that the methods that didn't work quite well introduced a lot of high-frequency noise in the data, which made it hard for the network to properly learn the right patterns to classify well. With so much high-frequency noise, the model might be forced to rely on lower frequency information, rely on them more, which can be throwing away too much information. Now let's do a check and see if these methods generalize to CIFAR 100 or whether there's anything different going on. As you might expect, the patterns of which methods work better is largely similar on CIFAR 100. So one slightly difference we found is that even more nonlinear methods beat the baseline mixed example methods, illustrating that at least some part of this is dataset dependent. Now, for a slightly more realistic dataset, I didn't go all the way to ImageNet for computational reasons, since I only had 2 GPUs. But look at this Caltech 256 instead. On Caltech 256, which has only 10,000 training examples over 250 categories in the data split I used the Inception V3 architecture and trained from scratch, which is a similar setup to ImageNet in terms of image size, but only takes 10 hours to train. As an overview of the result is on the right, and these were determined by a single training run for each method considered. One big takeaway is that any of the forms of mixed example data augmentation showed bigger gains over the baseline Inception V3, improving by roughly 10%. Within a mixed example methods, though, results were a little bit mixed. This could be due to dataset-specific issues, or might even be due to run-to-run variance in model training. In the end, VHBC Plus was a little bit better than the other methods here. In conclusion, in this work, we showed that linearity, if not essential for mixed example data augmentation, though it can help. We explored the space of mixed example data augmentation from an empirical perspective, and in doing so, also improve our existing state-of-art mixed example method. And thank you all for your time, and be here for the presentation before lunchtime. Thank you.
People who have questions, please come to the mic in the hallway. Yes, please. So my understanding is that you still used a classification loss to train this, but with the mix-up, it seems like you could also use a segmentation loss. Have you considered that?
I haven't tried that, but I also tried to reproduce the result from original mix-up paper and BC+, so to compare the final accuracy, but I haven't tried the other form of loss.
Yeah,
Yeah, if that's what you ask. Thank you.